For more videos like this for Compact 211, you can check out Sarai Studies. Link is in the description box below. In the last two videos, we have covered how to go from decimal to binary and vice versa. And now we have to cover octal, hexadecimal, and BCD. Remember that these are just number systems. They're different ways to represent the same number, just like we have different languages to represent the same word. So our goal here is to write the decimal number 156 in octal, in hexadecimal, and in BCD. So this notation means that 156 is in base 10. Base 10 is just another name for decimal because deci means 10. And you want to train your brain so that anytime you see the words octal and hexadecimal, you think I have to convert whatever they want me to convert from into binary. And I already recorded a video specifically on how to convert 156 to binary using two methods. So go watch that video if you need to first, and then come back and we'll start this. The link will be in the description box below, and also the video will pop up right here in the top right corner. So now that we have 156 in binary in base 2, I'm just going to bring that number down here. And the whole idea is when you see octal, you want to make groups of 3. And again, the right side to start on is on the right side. So here's the right side. So we're starting here and then we're going this way. So the first group of 3 that I see is this one. The second group of 3 I see is this one. The third group of 3 I see is this one. There's nothing here, so how do we represent nothing? With a 0, but we don't really have to write it. Now the first question is, why groups of 3? Well, in the same way that another name for the decimal number system is base 10, so 10 for deci, because that's what deci means, 10. And the same way that another name for the binary number system is base 2, so 2 for bi, because bi means 2, we can say that another name for the octal number system is base 8 for octal, because octal means 8. And so what do we do with this number 8? Well, we say 2 to the what power is equal to 8? And the answer is 3, which is why we make groups of 3. And it's the same pattern for hexadecimal. Hexa means 6. Deci means 10. 6 plus 10, that's 16. So here we'll have 16. 2 to the what power is 16? 4. So that means with hexadecimal, we're going to be making groups of 4. And here we'll be making groups of 3. It's whatever this exponent is. That's how many bits you're going to have in each of your groups. So now we have some groups of binary numbers. So each of these groups are going to give you an octal number. To find these octal numbers, I do what I like to call my conversion table. If you have GABA for the exams, he allows you to bring a couple pages of notes, so maybe this is something you want to have on there. So this is how I do it. The name tells you everything. Octal means 8. That means you're just going to do the first 8 numbers that you learned in kindergarten. What are those? Well, we start with 0. 1, 2, 3, 4, 5, 6, 7. So 7 numbers plus 1 more, that's 8. Now how many bits do we need? 3. But my table is for both octal and hexadecimal, so I know that here I'll need 4 bits. So even though I don't need 4 bits here, instead of having 3, I'm going to have 4, so I can join everything here. That means I'm going to have 4 place values. And the idea is that you're going to be here, this is all going to be binary. And binary by 2 powers of 2. So the place values are going to be powers of 2. You start on the right side. The right side is always the right side to start from. So 2, and then we're programmers, we start counting from 0 to the 0, 2 to the first, 2 to the second, 2 to the third. I stop here because those are 4 place values for the 4 bits that I want. 2 to the 0 is 1, this is 2, this is 4, this is 8. Then I fill in the table. How? Well, you ask yourself, how can I represent the number 0? Well, I would need 0 of these, 0 of these, 0 of these, and 0 of these. How can I represent the number 1? Well, I would want 1, 1, and then 0 of everything else. How can I represent the number 2? Well, I would want 1, 2, and then 0 of everything else. How can I represent the number 3? Well, I would want 1, 2, and 1, 1, because 2 plus 1 is going to give me 3, and everything else will be 0. How can I represent the number 4? Well, I would just want 1, 4, and everything else have it be 0. How can I represent the number 5? Well, I can do 1, 4, and 1, 1, because 4 plus 1 is going to give me 5, and everything else will be 0. How can I represent the number 6? Well, I can do 1, 4, and 1, 2, because 4 plus 2 is going to give me 6, and 0 of everything else. How can I represent the number 7? Well, I need 0 8s because that would obviously be more than 7. I'll do 1, 4. I'll do 1, 2 because 4 plus 2 is going to give me 6. And then I just need 1 more to give me 7. So 1, 1 is going to give me 4 plus 2 plus 1 is 7. Now this is all you'll ever need when working with octal. So then now you just try to find your groups. So really we read this as 0, 0, 1 because we start from the right these numbers, but I'm just going to read them as we read normally, but just know that. So we're looking for 1, 0, 0. 1, 0, 0 is here. And what is that in octal? That's 4.
Now we're looking for 0, 1, 1. 0, 1, 1 is right here.
And what is 0, 1, 1 in octal? That's 3.
So this becomes 3. And then we're looking for 0, 1, 0 because there's nothing there. How do you represent nothing with a 0?
010 is right here. And what is that in octal? That's 2. So we have 2 here. So just to sum it up, these are octal numbers and each octal number corresponds to a binary number. In other words, we're saying that 156 in octal is 234. And that's the notation we use, base 8. Now we're told to write 156 in hexadecimal. But 156 is in base 10. We want to convert it to binary. This is what it is in binary. So let's take that number over here. And in hexadecimal, we make groups of 4. So octal, 3. Hexadecimal, 4. Starting from the right. Why? Because the right side is the right side to start from. So we're starting here and then going this way, making groups of 4. So the first group of 4 I see is this one. The second group of 4 I see is this one. And again, we have binary numbers, so we have to figure out what hexadecimal values do these binary numbers correspond to. You don't ever have to memorize this. It's literally in the name. Hexadeci means 16. That means that you can only have 16 options, 16 of these. And with hexadecimal, if it was its own table, we start counting by 0, and then we're literally just going to go up until 16. So 3, 4, 5, 6, 7, 8, 9. But here's the thing. We have 16 options, but not all of them are numbers. So hexadecimal stops at 9, and once it gets to 10, it starts the alphabet. So then it's A, B, C, D, E, and then it ends at F. So you only really have to remember that the alphabet starts at 10. So to clear things up a bit, this is the octal table. And this is the hexadecimal table. So the idea is that we're going from binary to hexadecimal. So these are hexadecimal values, but we're missing some binaries. So what this is saying is, okay, if I see 0000, the hex code for that is going to be 0. If I see 0011, the hex code for that is going to be 3. But what should I see if the hex code is 9? Or what should I see if the hex code is 8? So all you have to do is find these binary values, which you just get by continuing your numbers. So I'll do 8, 9, 10, 11, 12, 13, 14, and 15. And it's the same process again. How can I represent 8? Well, I would need 1, 8, and everything else should be 0. How can I represent 9? Well, I would need 1, 8, and then 1, 1, because 8 plus 1 is 9, and then everything else should be 0. How can I represent 10? What about 10? Well, I need 1, 8, and then 1, 2, because 8 plus 2 is 10, and everything else will be 0. For 11, I would need 1, 8, 0, 4s, because that would go over 11, 1, 2, so 8 plus 2, that brings us to 10, and then 1, 1. For 12, I'll need 1, 8, and then 1, 4, because 8 plus 4 is 12, and everything else would be 0, because then we need 0, 2s and 0, 1s, because we already have 12. For 13, 1, 8, 1, 4, because this is 12, and then 1 more, so 1 of 1, and that's going to be 13, so 1, 1, 0, 1. For 14, I'll need 1, 8, 1, 4, so this is 12 already. I need 2 more, so just 1, 2. You add all of those together, and that gives me 14, and then 0, 1s, because I already have 14 with this. And then finally, 15 is going to be 1, 8, 1, 4, that's already 12, 1, 2, that's going to be 14, and then 1, 1 is going to give me plus 1, that's 15. So they're all 1s. So now we're ready to translate. What is 1100? Well, you go and look for it in your red box. 1100 is right here. And what is its hex code? C. The hex code, these are the hex codes, is C. Now what's 1001? 1001, the hex code is 9. And that's it. So we're saying that 156 in hexadecimal is 9C, and the notation is base 16, because base 16 and hexadecimal are the same names for the same number system. So now we're done with octal and hexadecimal. And lastly, let's work on writing 156 in BCD. Just take what they want you to convert, which is 156, and all you're doing is taking each digit and finding what it is in binary. That's it. And the idea is that because any number in decimal can only be written with the digits 0 to 9, then those are the only digits that you're going to be dealing with, the digits from 0 to 9, and whatever their binary values are. So you're either going to see 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Like, that's it. In this case, we see 1, 5, and 6. 1, 5, and 6. That's what we see. You'll never see anything like 11, 12. No, because the whole idea is we take every single digit individually, not 56 and what that is in binary. So here we have 6, so we're going to go here to find where 6 is. What is its corresponding BCD code? It's 0, 1, 1, 0. Then we have 5. You find where 5 is. 5 is right over here. It's 0, 1, 0, 1. So 0, 1, 0, 1 is going to go here. And finally, what is 1? Well, you search for 1, it's right here. It's 0, 0, 0, 1. So here it's going to be 0, 0, 0, 1. So putting it all together, if we get these a little bit closer to each other, we say that this is our BCD, our binary coded decimal. And just to make things clear on the table, since we're only looking at digits from 0 to 9, because that's all of the digits we're ever going to see, either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, then our BCD part of the table is this part. So when we're working with BCD, we're literally just looking at this.